All right, so in section 4, you're going to learn 2 more tests. They're called the comparison tests. There's 2 of them. Really what we're going to do, just the big idea of this section, is that you're going to find something to compare a series to. Okay? That's why they're called the comparison tests. Cool? So let's just kind of have a hypothetical example, and then that will lead us to come up with like a definition of what we're going to do here. Cool? All right, so let's say, consider the following series. So let's say that you have a series like this, from 0 to infinity, of 1 over 3 to the n power plus n. Okay? And let's consider all of the tests that you've already learned thus far. Cool? So the first of all, let's talk this through. Is this geometric? No. So that one kind of goes out the window, right? Could I make this telescoping? Is there a way that I could partially fraction decompose this? No, this is not then telescoping, right? I could do the nth term test. The nth term test tells me to take the limit as n goes to infinity, which would give me a 0. And that just means that it's inconclusive, and it just tells you, hey, go try something else. Agreed? Is this a p-series? Nope. What is the last thing we could try? That we have learned. The integral test. So, I mean, I could say let f of x equal 1 over 3 to the x plus x, right? And then I could take the integral from 0 to infinity of 1 over 3 to the x plus x dx. You guys with me? I don't like where this is going, and neither should you. That doesn't look very simple to do, right? And remember, the integral test, I first have to check, is it positive? Is it continuous? Is it what else? Decreasing. And then if it meets all those requirements, then I can take the integral, right? You guys with me? However, I mean, I'm just looking at this. How are you guys going to integrate this? Right? So, if you remember, last class I said, the integral test is the one that you want to try last. That's your last resort. Cool? So today we're going to try to explore if there is a way to maybe not use the integral test so that we could go and apply something else, which in this case what we're trying to discover today are called the comparison tests. Cool? And then I actually had someone in, I think, Jameson Donahue try this on the calculator yesterday, and it took, like, the calculator was just loading and loading and loading and loading and loading and loading. Because the 89s do have an infinity. You guys do know that, right? I don't think he ever got an answer, so it was like 30 minutes loading and he never got an answer. Cool? But anyways, so here's what we're going to do, okay? There's a few things that I want you to notice. First of all, do you guys notice that this right here, this part, is a sequence, right? You need a sequence in order to have a series. Cool? Do you notice that all of the terms of that sequence would be positive based on what I gave you here? Yes? Cool. Here's what we're going to do. Let's pretend that I drop this n value right here. Sorry. That I just get rid of this n value. What I would have then is that. You guys with me? If I just completely drop that plus n. You guys with? And when I look at that series, that's a very easy series to deal with. It's a geometric series. Because I could just rewrite this as the series like that, which is the same thing. You guys with me? And that's geometric. And according to, if I have a geometric series, if this value right here, which is r, if r, or the absolute value of r is less than 1, then what do we know? It converges. So, here's what I could say. I could say that, for the moment I don't really care what it converges to. That series right there converges because it's geometric and the rate is less than 1. But that's not what the question was, right? The question was whether this series converge. Well, let me ask you something. What happens if I ask you to compare what I originally gave you versus that new series that we just kind of stumbled upon? Well, what you think this through? We've already discovered that this converge, right? Here's my question. Do you think that this series right here, this series right here, compared to this series, which series would be bigger and why? The right would be bigger? Why? If you add an extra number to that 3n, that makes the denominator bigger. Do you guys agree? And having a denominator that's bigger makes the fraction smaller. So that means that this fraction is bigger than this fraction. And here's the cool thing. I'm not saying that this is what the graph looks like, but let's just pretend that the summation graph of this looks like this. And so on, right? It's got to be increased because it's increasing because it's summation, right? And that's let's call this one b sub n, just for the sake of it. Okay, let's call that's b sub n. Well, according to what you just told me, a sub n would have to be below it because it's smaller for its entire domain. So if you know that the bigger one converges, what could you tell me about something that's smaller? It's going to converge. And that's the big idea here. We're going to try to find a series to compare it to. If we can find a series to compare it to, we can make a decision whether or not something is going to converge or diverge by basically not even attacking the series that I gave you, but attacking the series that you're comparing it to. Cool? Are we okay with what's going to happen in this section? Yes, sir. Right. So how do you know you're comparing the right? How do you know what to compare it to? Yeah. Cool. So we're going to practice some examples, so hopefully I'll share some tips with you as we move along so you understand what it is we're going to compare it to. Cool? All right. So let me go ahead and give you like an official definition of this. Okay? So if you're watching the video, I'm just going to go ahead and project it and then pause the video and write it down, and then when you're ready, hit play. So here's the official definition for you guys. Cool? So I'm going to go ahead and pause the video, please. Alright guys, just real quick, if you're watching the video, I just realized I made a mistake. We want to go ahead and switch this to this is a sub n, and that's b sub n. Alright, so here's what the direct comparison test tells you. So first of all, let's suppose that you have two series. We're just calling it a sub n and b sub n. No, I did not forget to write the infinity. It is stated that when you write a series like this without having a lower and upper bound or index, it's an infinite series. Cool? So you have two infinite series with both of them being positive. So that's important for this test. So they have to be positive, okay, for all of the n values. And one of those series has to be either less than or equal to the other series. Cool? For all the n values. Then the following happens. If the bigger series is convergent, then so is going to be the smaller series, right? So if b sub n, so if the bigger series is convergent, then that means that the smaller has to converge. The opposite is if a sub n is divergent, so if the smaller series diverges, then the bigger series also has to diverge. Cool? And that's essentially what I'm telling you here, okay? So you're just going to compare the two series. But there's always got to be one smaller and one bigger. And depending on the scenario, you're going to determine convergence or divergence. Cool? Alright, let's do our first example. So first example is determine the convergence or the divergence of the following series. So we've got a series from 1 to infinity, bless you, of n over n squared minus cosine square of n. Now remember, at some point, you're just going to be given series, and you're going to know all of the tests. And it's going to be your task to figure out which is the best test to apply, right? The test that you should always apply first is which one? The Nth Term Test. Cool. Well, if we apply the Nth Term Test here, you should realize that this is going to be equal to 0 because of the degree on the denominator being bigger by the rules of asymptotes. So 0 just means inconclusive, right? This is definitely not geometric. This is definitely not a p-series. Okay, we could try the integral test, but I don't like this. So now we have this new test called the direct comparison test. The question is, how do I find out what to compare it to? And that's where you're going to have to analyze, and really your knowledge of mathematics is going to just help you out here, your common sense. Okay? As this number approaches that, right, there's one term in here that it's not really going to make a difference. The cosine square. Why? It's oscillating between what values? -1 and 1. So you're either adding or subtracting 1. And as you're getting bigger and bigger and bigger and bigger, is that really going to matter? No. So what are you going to compare it to? That. We're going to drop this term. It's not necessary. Say that one more time. Correct. So it's not going to make a difference, right? As that number gets bigger and bigger and bigger, taking 1 away from it, not going to make a difference. Cool? All right, so this is what I'm comparing it to. And look, even better, it reduces. It reduces to this series known as the harmonic series. And we discovered last class that the harmonic series is technically a p-series, right? What happens to it? Diverges. So this diverges by the p-series, right? So it's going to be important for you to write this down, okay? Why you know that that's divergent. Now the task is, when you look at this series, or this sequence, sorry, versus this sequence, I'm going to go ahead and go back to this statement right here. Cool. Which one's bigger? The one on the right is bigger? Because if I'm subtracting 1, that makes this a smaller, which makes this a bigger fraction. So what that means is that this is bigger. Agreed? So let's think this through. If what we're comparing it to, which is in this case this is the non-reduced form of it, is diverging, and this is bigger than that, what does that mean about this? That is going to diverge as well. Therefore, the series from 1 to infinity of n over n squared minus cosine square n diverges by the direct comparison test. And that's how easy it is to use this test. You with me? You typically want to find something that whatever you're comparing it is something that you can find whether it converges or diverges very easily. If you're going to compare it to something that you can't even figure out what it is happening, then the comparison test is not really the way to go. Cool? Questions about this one? We're good? Okay. Let's try another one. So we're going to go from 1 to infinity of n squared plus 2 over n to the 4th power plus 5. Uh-oh. All right. Why is it? What do you guys think? It's not geometric. It's not a p-series. Nth term test is going to get us what? 0. Inconclusive. Integral test, maybe. I don't know. Comparison test. Could I use a comparison test? Yes? What could I compare it to? I would say n squared over n to the 4th, and then you can reduce it, right? Adding 5 or adding 2 as those numbers are getting bigger and bigger does not make a difference. Cool? Now, if you reduce that, you're technically comparing it to what? 1 over n squared, which is very easy to tell me whether it converges or diverges. It converges. Why? So if you're watching this video and you don't know what the p-series is, the p-series says that if you have a series that looks like this, if the p-value, which is the exponent, is greater than 1, what happens to it? It converges. If the p-value is less than or equal to 1, it diverges. In this case, it's greater than 1, and that's why we know that this series converges. Cool? So now the question is, we need to prove, in order for us to say that this converges, this needs to be what? Smaller than this. Agreed? Okay, so then the question is this series is it smaller, less than or equal to this series? I always like to go back to the unsimplified version to make my life easier. Is it smaller? Why? Bigger denominator means smaller fraction. But what about that too? It doesn't matter, guys. Like, as we get very large, adding 2 is that going to make a difference? No. Bigger denominator means smaller fraction. So yes, indeed, it is smaller. Therefore what? The series that we started with, which is converges by, and I get lazy, so sometimes I just do this, DCT, direct comparison test. Cool? Are we okay? This is a pretty easy test to apply. Cool? Alright, I hope we're realizing that. I know so far we've got like, what, 5 or 6 tests under our pockets. It's not difficult. It's just a lot of tests and a lot of little details to remember. Cool? Alright, let's try one more thing. So same instructions. Let's say we want to determine whether it converges or diverges. Of that. Well, we kind of already did this problem, sort of. Yes? We did this problem, but we did this problem with a plus. So we've got kind of half of the problem already done. What did we compare this to? The 1 over 3n, which was geometric, right? Which means that it converged because the rate was 1/3. But the question is, if we do in fact compare this series right here versus the series (1 over 3n), which again we've already done this. This is geometric; it converges. Which one's bigger? The left. Yes? So if this is bigger than this, well, we don't know that. And that's why I wanted to bring that up. We know that this converges, right? Something bigger than it could still converge. It could diverge. We don't know. We don't have that guarantee. So just because he failed the direct comparison test, so this is one example where we failed the direct comparison test, that's not enough information for me to say that it diverges. Cool? This converges and it's smaller than something bigger. This could potentially, maybe, still converge. We don't know that for sure. Understood? So the direct comparison test failed for us, so we got to try something else. Does that mean we need to turn into the integral test? Maybe, but there's more tests. So let's discover another test. Okay? The other test is called the limit comparison test. So go ahead and project that, and here's what the limit comparison test says. So if you're watching the video, go ahead and pause it, write it down, and when you're ready to go, hit play once again. Alright, so I'm assuming you gave it a go and you went ahead and wrote it down. So let's just kind of talk about what the limit comparison test says. So just like the direct comparison, you still have two infinite series, and they're still positive for all n. But here's where the things get interesting. So this is called the limit comparison because what you're going to do is essentially you're going to take whatever series I gave you and whatever series you're comparing it to, and you're just going to divide them. Now, I wrote it this way, but what I want to say is that it doesn't matter which order you do it. You could have done b sub n divided by a sub n. It doesn't matter. Okay, so there is no order in which you do the ratio of the two. Okay, but here's what it says. If you take the limit of that going to infinity, and you get some c value, whatever that value is, okay? So if you get infinity, that means it doesn't work. Cool? So you got to get a value out of it. If that value is positive, and if that value is finite, right, so not infinity, then both of them are either going to converge or diverge. Whatever it is that you compared it to. So if you whatever you compared it to diverge, then that means that if you use the limit test and it passes the limit test, then it also diverges. Or if what you're comparing it to converges, then so does the one that I originally gave you to. Cool? Most people like the limit comparison test or prefer this one versus the direct comparison because you don't have to find out what's bigger or what is smaller. Cool? Yes, sir. Yes, so let's go back to the example we were working on that was inconclusive with the direct comparison. So we were on this one and we were inconclusive with direct comparison. Yes? So how about now we apply the limit comparison test? So the limit comparison test, that means that I'm going to take the limit as n approaches infinity of the ratio of the two series. So here's the original series that I gave you, and here's what we want to compare it to. The order in which you do this does not matter. So let's just do, I don't know, the original. So 1 over 3 to the n minus n divided by 1 over 3 to the n. Cool? We're going to take that limit. Well, let's just do some algebra before we actually take the limit. So we're going to say the limit as n approaches infinity of 1 over 3 to the n minus n times 3 to the n over 1, right? You guys with me? Which is simply the limit as n approaches infinity of 3 to the n over 3 to the n minus n. Cool? Alright. What happens here? The limit as n goes to infinity. Well, if we take the limit as n goes to infinity of 3 to the n and divide that by the limit as n goes to infinity of 3 to the n minus n, we obtain infinity over infinity, which is not 1. What does it mean? L'Hopital's rule comes into play. Cool? So I chose this example on purpose to practice the L'Hopital's rule. I know the AP exam is around the corner. So, and also because I need to make sure that you haven't forgotten how to take the derivative of something like that. Remember, so it's the natural log of the base times itself times the derivative of the exponent, which in this case is just a 1. You guys with me? Okay. So isn't that what's going to happen on the denominator as well? So we're going to have ln 3n, but we're going to subtract 1. You guys agree? Well, if I apply the limit again, that would be like the limit as n goes to infinity of ln of 3 times 3 to the n over the limit as n goes to infinity of ln 3 to the n minus 1. What happens? I still get infinity over infinity. I don't think so. I think I can do L'Hopital's one more time. Because here's our problem, guys. If I take the derivative one more time of this, I'm going to get the same thing as this, right? But what's going to happen to this? It's going to go away. Right? So just to practice, can we take one more derivative? Okay, so go ahead and flip the page. So we had, what do we have? ln 3, right? And then 3n. Cool. Over ln 3n minus 1. Okay? So we got the limit as n approaches infinity. Well, it's not really a product rule because ln of 3 is just a number. You guys with me? Okay. So we're going to say ln of 3 times the derivative of this, which the derivative of that we've already found. What's the derivative of 3n? ln 3 times 3 to the n. Agreed? And that's going to be the same thing on the denominator. ln 3 times ln 3 to the n. And the derivative of that 1 goes away. Well, that looks all complicated, but if we just use algebra, if we have the same thing on top and bottom, what does that mean? So what is the limit as n approaches infinity of 1? 1. Okay, so let's not forget, we were doing what? We were doing the limit comparison test, right? Which means that the limit that we got was c, like a c value, right? 1. Is 1 positive? Cool. Is it finite? Fantastic. So what does that mean according to the limit comparison test? Well, the limit comparison test says if it is that, then they both either converge or diverge. Well, what was the one that we were comparing it to? Well, this one right here. And what does that do? It converges by the geometric test, right? So if that converges, then therefore the series from 1 to infinity of, what was it? 1 over converges by limit comparison test. Cool? Questions? Do we understand what happened with the limit comparison test, what it does for us? I personally prefer the limit comparison. If I'm going to use the comparison test, I prefer the limit personally. Okay? You don't have to use one or the other, whichever you like or whichever you feel more comfortable with. Okay? So, just for the sake of this video, we're just going to close out with one more example. Okay? So, if you're watching this video, I want you to give it a go on your own, and then when you're ready, just hit play, and then I'll show the response. So, if you're in class, just go ahead and try this one on your own. So, we're going to determine the convergence or the divergence of the following series. From 1 to infinity of 3n squared plus 2 divided by n squared minus 5 square. So give it a shot, see what you can come up with, and when you're ready, just hit play. Alright, so I'm assuming you already gave it a go. So here's what I tried. So first of all, I expanded out the denominator so that I could get this. Okay. When you are deciding what to compare it to, really what you want to look at is what is the most dominant term on the numerator and what is the most dominant term on the denominator. And the most dominant term really is the n squared and the n to the 4th. I didn't really keep the 3 because as we go to infinity, it's really not going to make much of a difference. So I just decided to keep the n squared and the n to the 4th, which reduces to be 1 over n squared, which converges by a p-series. Okay? And then I applied the limit comparison test. So I took my original, and then divided it by what I'm comparing it to, which is the same thing as multiplying by the reciprocal. And here's what I get. The denominator and the numerator are exactly the same, which means that by the rules of asymptotes, as I go to infinity, it should be the division of the leading coefficients, which in this case is 3 over 1, which is 3. 3 is positive, 3 is finite. Therefore, since that converges, the original series also converges by the limit comparison test. Cool? Alright, so that brings an end to this lesson. So far, then, you've learned about 6 or 7 tests. Cool? If you have any questions, just shoot me an email if you have any questions over the weekend. And then, if you're just watching the video, thank you for watching.